This video is part 2 of our series of transformations of functions. In this lesson, you learn about horizontal and vertical stretches, compressions, and reflections. In the last lesson, we learned how to apply vertical and horizontal translations to our parent function, and by the end of the lesson, you'll be able to apply vertical and horizontal stretches, compressions, and reflections to our parent function as well. You'll be able to appropriately name the transformations of functions, and you'll be able to create the equation of a function when the parent function and the transformations are given. We're going to start with our vertical stretches and compressions, and we're going to use the square root function as our parent function. So I'd like you to graph all 4 of these functions into decimals and then draw your graphs right here. Here we have all of our functions graphed. So our red function is our parent function, y equals the square root of x, and our green function is y equals 2 root x. Our blue function is y equals 1 over 2 root x, and our orange function is y equals negative 2 root x. So let's compare all of our functions with our parent function. So this green function right here, y equals 2 root x, that's a lot bigger than this parent function. And if we look at the equation, y equals 2 root x, 2 is being multiplied by our parent function. But I want to pay close attention to where that 2 is located. Notice how it's on the outside of the function, not inside this square root symbol. So remember from last video, when we had a function and we added or subtracted a number from that function, but it was outside of the function, it was not inside the function, this moved our functions up or down, so these were vertical translations. So when we added or subtracted a number outside of the function, it directly affected our y values. Now this 2, again, it is outside of our function, it's not inside this square root. So this is also going to directly affect our y values. So let's look at our graph. On our parent function, we have a y value here, that's 1. When we multiply that by 2, it gives you this new function right here. And at this point, our y value is 2. When we multiply the 2 by 2, we get 4, and that's our green function. And we multiply this point, 3, by 2, our new y value is 6, and that's again our green function. So let's do that with all of our other graphs. So our blue function, 1 over 2 root x, this is a vertical compression. All of our y values are going to be halved. So at this y value 1, instead of 1, it goes down to a half, and that's our blue function. At this y value of 2, multiplied by a half, that's now 1. And at this y value of 3, multiplied by a half, and that's 1.5, so again, that's our blue function. So this blue function was a compression. And let's look at this orange function. Notice that the orange function is pointing in a whole different direction. That's because of that negative, because we're multiplying by negative 2 here. So it looks like our green function, y equals 2 root x, but it's been flipped. And this would be a reflection in this x-axis. So instead of multiplying by just 2, we're multiplying by negative 2. So 1 multiplied by negative 2, you get negative 2, and that's why that point is down here. And this y value of 2 multiplied by negative 2, you get negative 4, and that's again our orange function. And when we have 3 multiplied by negative 2, that gives us negative 6, and that's from our orange function right here. So let's summarize this. So when we have our parent function and we're multiplying that parent function by a number and the number is outside of the function, we use the letter a to represent that number. So when a is greater than 0, so when it's a positive number, there is no reflection. And when a is a negative number, the function is reflected in the x-axis. So we can see that in our examples above. A is positive in our green function and in our blue function, and there is no reflection. But there is a reflection in this orange function right here, and that's because our a value is -2. So let's look at when we have a vertical stretch or compression, and we're going to look at the absolute value of a, because we already know when a is less than 0, when it's a negative number, our function is reflected in the x-axis. So when the absolute value of a is greater than 1, our function is vertically stretched. And when the absolute value of a is less than 1, the function is vertically compressed. And we use this word vertically because this a value, remember, it's on the outside of the function, and this directly affects our y values. So now let's look at some horizontal stretches and compressions. And I want you to, again, take these functions, they're different from our other ones, and I want you to graph them into Desmos and draw all your graphs right here. So here are all 4 functions graphed. And let's label these. So our red function is our parent function, y equals the square root of x. And our green function is y equals square root of 2x. Our blue function is y equals the square root of 1 over 2x. And our orange function on the left is y equals the square root of -2x. Now let's look at these and look at the placements of all of our numbers. So we are again multiplying by a number, but where is that number located? It is on the inside of our function, underneath the square root. And if you remember from our last video, when we had a function and we added or subtracted a number inside that function, inside that parent function, then it directly affected our x values. So these numbers, since they are directly inside of our functions, they're inside that root, it's going to directly affect our x values. So let's look at these points. So if we look at the green graph, y equals the square root of 2x, it does look like it has been stretched because it's higher than our parent function here. But in fact, the opposite has happened. It wasn't really stretched because we're looking at our x values. And if we look at our points, so if we have this point right here, our y values are not changing in our points. And in the green graph, this is the new x value. So in fact, the green graph has not been stretched, it's been compressed. So let's look at another point right here. So this point, again, the y values have not been changed, has gone down here. And if we look at this x value at 9, our new x value in our transformed graph is actually right here. So our green graph, in fact, has been compressed. And to really understand this, so remember that when it's within the function, it's inside the square root, it's inside the function, it directly affects our x values. And to really see this, we need to rewrite this in terms of x, because again, all of these are in terms of y, if you remember from our last video. These all have y equals the square root of x. So if we rewrite this in terms of x, meaning we want it to say x equals, we would need to then isolate x. So to get x on its own, we need to get rid of the square root. So we would just do the opposite, which is squaring y. And then to get rid of this 2, because x is being multiplied by 2, and the opposite of multiplication is division. So it would be this whole thing divided by 2. So realistically, we are taking all of our values and dividing by 2. So that is what's happening here. Our graph is being compressed because all of our original x values are being divided by 2. So if you look at our actual points, our x value in the original graph here is 1 divided by 2, you get a half. And the x value in this original point is 4. 4 divided by 2 is 2, and we get our transformed function. And in this point right here, our original x value is 9, and when we divide by 2, we get 4.5. And that's how this green function came out to be. So if we look at our blue function, inside that square root, we have 1 over 2x. X is being multiplied by 1 over 2, or in other words, x is being divided by 2. And if we want to look at this in terms of x, so this is our equation in terms of y, square root of 1 over 2x, and we want to get this in terms of x. So we need to isolate x. Remember, we have x is equal to y squared, and we have that 1 over 2 here. Now the opposite of that is just multiplying by 2. So x is equal to 2y squared. So all of our x values are actually being multiplied by 2 in our blue graph. So let's look at our points. We have all of these points here, and we're going to compare them. So all of our x values are actually being multiplied by 2. So at this point, our x value is 1, and 1 times 2 is 2, so that point gets moved over here. And this point, our x value is 4, and 4 times 2 is 8, and that point gets moved over here. And we can't actually see the transformation of this point, but it would be at 18 because 9 times 2 is 18, so that's just off our graph. So in our function, y equals the square root of 1 over 2x, this is actually a horizontal stretch because all of our points have stretched. All of our x values have been multiplied by 2. And in our last graph, y equals the square root of negative 2x. It's similar to our green graph right here because our green graph is y equals the square root of 2x, but notice orange has a negative here. Instead of 2, it's a negative 2. So similar to our green graph, instead of multiplying by 2, it's kind of the opposite. We're dividing all of our x values by 2, but because of that negative, we're dividing all of our x values by negative 2. So that shows that there is a reflection here. There is a horizontal reflection, and this horizontal reflection is in the y-axis. And if we want to compare our points, this 1 in our parent function, 1 divided by negative 2 is just a negative in half, and that's why it's on this side. And 4 divided by negative 2 is negative 2. That's why it's on our left side. And then 9 divided by negative 2 is negative 4.5, which gives us that reflection in the y-axis. So to summarize this, when we have a number inside of our function that we're multiplying or dividing by x, we use the letter k. So when k is greater than 0, when it's a positive number, there is no reflection at all. And when k is less than 0, when it's a negative number, the function is reflected, but now it's reflected in the y-axis instead of the x-axis. So we're going to look at the absolute value of k. So when k is greater than 1, the function is actually horizontally compressed. So we can see that in our graph, in the green graph, y equals the square root of 2x. When the absolute value of k is greater than 1, so in this case it's 2, there is a horizontal compression. So I know it does look a little stretched, but when we actually compare x values in our points, they've all been halved. So they've all been divided by 2, so they have been compressed. And when the absolute value is less than 1, there is a horizontal stretch. And we're going to see that in our blue graph, y equals the square root of 1 over 2x. So when we compare our x values and our points, they're all doubled. So this graph has been horizontally stretched. So let's just summarize all of this again. So when we are multiplying our function by a number and it's on the outside of our function, that's affecting our y coordinates. And when we are multiplying by a function and it's inside of the function, that's directly going to affect our x coordinates. So A, it's outside of our function. It represents all vertical stretches, compressions, and reflections. When A is greater than 0, there is no reflection. When A is less than 0, there is a reflection, and that's in the x-axis. When the absolute value of A is greater than 1, the function is vertically stretched by a factor of A. So this wording is very important when we start describing our transformations. And then when the absolute value of A is less than 1, the function is vertically compressed by a factor of A. So now looking at the letter K, so K is inside of our function, so this should be K instead of H. And remember, this is when we multiply by a number inside our function. So K represents the horizontal stretches, compressions, and reflections. When K is greater than 0, when it's a positive number, there is no reflection at all. And when K is less than 0, when it's a negative number, it's reflected in the y-axis this time. So when K is greater than 1, there's a horizontal compression by a factor of 1 over K. So this is opposite of A, because when A is greater than 1, it's a vertical stretch. And when K is greater than 1, it's a horizontal compression. And we use this particular wording by a factor of 1 over K. So if we remember from our graph, y equals the square root of 2x, this graph, it wasn't stretched by a factor of 2. We were actually dividing all of our x values by 2. So all of our x values were compressed by a factor of 1 over 2. And when the absolute value of K is less than 1, there's a horizontal stretch by a factor of 1 over K. So that again is important. So from our other example, when we had the function y equals the square root of 1 over 2x, we were multiplying all of our x values, all of our x coordinates, by not 1 over 2, by the reciprocal. So we were multiplying by 2. So it was a horizontal stretch by a factor of 2. So just to make a little note, when we have an a value and we're multiplying our function by an a value, we're going to multiply the y-coordinate by a. Or when we have a k that's inside of the function that affects our horizontal stretch or compression, we're actually going to multiply our x-coordinate by 1 over k. Or in other words, we're going to divide that x-coordinate by k. So in this example, we're going to describe the transformations of these different functions, and we're going to use this equation. So we know that A affects the vertical stretches, compressions, and reflections. K is inside this function and affects the horizontal stretches, compressions, and reflections. Our D from the last video is inside the function as well, and it also affects the horizontal shifts. And C outside of the function affects our vertical shifts. So looking at our first function, we need to identify what the parent function is. So it has a cube, so it must be our cubic function. And now we need to identify what the transformations are. So this 1 over 3, it's outside of the function, so it must be our a value. And since this a value is less than 1, that means we have a vertical compression by a factor of 1 over 3. And if we look inside the brackets, we have a negative here. So this can't be this d. It's actually our k, so this is a negative 1, and this is our k value. And since k is equal to negative 1, there is no stretch or compression, but there is a horizontal reflection in the y-axis. And our last number here is this minus 1. Since it's outside of the cube, it's outside of the function, that must be our c value. And since it's a minus 1, our function is going to shift 1 unit down. So we're going to make a t-chart of these transformations, just describing what happens to all of our coordinates. So our original coordinates are x and y. And we're going to look at what happens to all the x coordinates and all the y coordinates. So the only part of the function that affects our x coordinate is the k, because we do not have a d value. So k is equal to -1. So all x coordinates will be divided by -1. And when we look at what happens to our y coordinates, we have an a and a c that will affect our y coordinates. So since a is equal to 1 over 3, all y coordinates are going to be multiplied by 1 over 3 and then subtracted by 1, because the entire graph will shift 1 unit down. So in our next example, the function is y equals 4 over x plus 2. Now this must be the reciprocal function because we have a fraction and x is on the bottom. So our parent function is in fact the reciprocal function. And it might be difficult to see where the transformations are, how to identify them. So I'm just going to rewrite this function as y equals 4 times 1 over x plus 2. So now it might be a little bit easier to identify what each number represent and what the transformations are. So 4 is actually our a value. So that means we have a vertical stretch by a factor of 4. And this plus 2 is actually our d, except d is not a positive 2, it's actually a negative 2, because remember our function from our last video is x minus d. When we put in a -2 into that d, it becomes x plus 2, which is what we have here in our function. So this is going to be a horizontal shift of 2 units to the left. Now try making a t-chart on your own, showing the explicit transformations to your coordinates. And if you made that t-chart, it should look like this. So we have x minus 2 because we have a horizontal shift 2 units to the left. And all of our y coordinates will be multiplied by 4 because our a value in this function is 4. So here's our next function, and let's identify that parent function. You can see those lines here, that's our absolute value symbols. So this is the absolute value function. And we need to identify these transformations. So on the outside of those absolute values in the front here, we have our a value. Our a value is -3. So that means two things are going to happen. The absolute value of 3 is bigger than 1, so that means we're going to have a vertical stretch by a factor of 3, but also it's negative, so that means there is a reflection in the x-axis. So inside our absolute value, we have two things going on here. X is being subtracted by 5, so our d value is actually 5. And also this whole thing is being multiplied by 1 over 2, so this is our k. So since k is 1 over 2, we're going to have a horizontal stretch by a factor of 2. And since 5 is being subtracted from x, our whole graph is going to shift to the right 5 units. And lastly, we have this plus 1 over 3 at the end. So this is our c value because it's outside of the function. And that means our whole function is going to be shifted up 1 over 3 units. So let's quickly make a t-table of our transformations. So we have x and y, our original coordinates. And we have our a value. A value is -3. So -3 affects our y values. So all y coordinates are being multiplied by -3. So next we have our k value, which is 1 over 2. And I know this whole thing looks like it's being multiplied by 1 over 2, but because we're just affecting the x, we're dividing our x by 1 over 2. And that is the same thing as taking your x and multiplying by 2. So 2 times x is the same thing as x divided by 1 over 2. So next we have D. So it says x minus 5 here, but we are doing the opposite because we're affecting the x coordinate. So x is actually equal to 5. So we're going to add 5 here to all of our x coordinates. And lastly, we have our c value. So c is equal to 1 over 3. And we're adding 1 over 3 to all of our y coordinates because our whole entire graph is shifting up 1 over 3 units. So now we're going to work on graphing these functions, these transformed functions. So again, A affects our vertical stretch and compressions. We're going to multiply all of our y values by A because that A is outside of the function. And then we have our K value. So K affects our horizontal stretch, compressions, and reflections. So K is within that parent function, so we're going to multiply all of our x values by 1 over k, or we're going to divide all of our x values by k. So this is going to give us the exact same result. And then we got our c value. So this affects our vertical translations, or vertical shifts. So we're going to add or subtract c to all of the y values. And then we have our d. So d is our horizontal translation, so that means we're just going to add or subtract d to all of our x values. Okay, so this is really going to help you figure out what you need to do to your x coordinates and your y coordinates to get your newly transformed graph. So we have our a value here and our c value. And those are outside of the functions again, and those directly affect our y coordinate. So a is always being multiplied by y, and then we're going to add or subtract whatever our c value is. And then inside, within our function, we have our k value and then our d value. So remember, you're going to take your x coordinates and divide by your k value, and then you're going to add or subtract whatever your d value is. So we got our function right here, and we got to identify the parent function. And our parent function is y is equal to x cubed. That's our cubic function because of that cubed there. So let's just make a t-table to organize how we're going to transform all of our x coordinates and our y coordinates. So our a value, we have our a value right here in front of our function, and our a value again affects our y coordinates. So since our a is -2, we're going to multiply all our y values, our y coordinates, by -2. So inside the brackets, inside our function, we're not multiplying x by anything, but we are doing x minus 4. So we have a d value here. So our d value is actually 4. So all of our x coordinates, we're going to add 4 to them. And then at the end here, after the cubed, we have plus 3. So this is our c value. So our c value is 3. And we need to add 3 to our y coordinates. So these are the transformations of what's going to happen to our original x and y coordinates of our parent function. So in the parent function, we need to identify some of our key points here. So in our parent function, if we start with an x value of -2, so -2 cubed is -8. And -1 cubed is going to be 1, or -1. 0 cubed is just 0. 1 cubed is 1. 2 cubed is a +8. And then 3 cubed is +27. But that won't fit on our graph, so we won't really have to transform that graph or that point. So I've graphed the original parent function, and now we need to apply these transformations to all of our original points to get our transformed points. So our first x coordinate, -2, we need to add 4 to it. So that's going to become +2. And then our y coordinate is -8, so we got to do -8 times -2, and that's +16. And then we need to add our c value. So our c value here is actually 3, so we need to change that to 3. So we're doing negative 8 times negative 2 plus 3, and that's going to be 19. So that point won't even fit on our graph. So I want you to pause this video and apply these transformations to the rest of the points here, and then check back to make sure you did it correctly. So I've written out the new points, and I've actually graphed our transformed function as well. So let's look at all of our transformations. So our a value is negative, and that means there is a reflection in the x-axis. So our graph was going from left to right, it was going up, but now from left to right, it's going down. So there was in fact a reflection in this x-axis. It was flipped along the x-axis, and there is a vertical stretch by a factor of 2. So these points have stretched by a factor of 2, and you can see here between these 2 points there's a difference in 1 unit, but in here there's a difference in 2 units. And our entire graph has moved over to the right 4 units. So if we look at this center point right here, 1, 2, 3, 4, it's gone to the right 4 units, and it's actually gone up 3 units. And if we want to determine the domain and range of this function, it doesn't actually change. So for cubic functions, our domain and range does not change. So x is an element of real numbers, and y is also an element of real numbers. So try this example on your own. Make sure you find all your transformed points and graph your function. And then I want you to input that function into decimals to make sure you did it correctly. We will be continuing this lesson and working on our transformations of all our parent functions in class.